You are listening to Bulletproof Next.js APIs, a guide to modern security architectures. Subscribe to keep up to date on our latest audiobooks. Bulletproof Next.js APIs, a guide to modern security architectures. 1. Introduction: the imperative of API security in Next.js. Imagine waking up to the headline: Major data breach exposes millions of user records. Or worse, realizing your own application, the one you painstakingly built with such care, is the source of the leak. In today's interconnected digital landscape, such scenarios are not distant threats. They are daily realities that can cripple businesses, erode user trust, and invite severe legal and financial repercussions. For years, the internet operated with a clear distinction between a web page and the complex machinery behind it. But the modern web is fundamentally different. It's dynamic, interactive, and powered by a constantly flowing stream of information. The invisible workhorses making all this possible are application programming interfaces, or APIs. From fetching your social media feed to processing an online payment, APIs are the digital conduits that allow different software components to communicate, share data, and perform functions. They are the backbone of virtually every application you interact with daily. This pervasive reliance on APIs means they have become prime targets for attackers. A misconfigured or unprotected API endpoint is no longer an isolated flaw. It's a wide-open gate to your most valuable assets: user data, intellectual property, and system integrity. Compromising an API can lead to data theft, unauthorized access, service disruptions, and even complete system takeovers. The stakes couldn't be higher. Enter Next.js, a powerful React framework that has revolutionized web development. Next.js offers an incredible blend of front-end reactivity and server-side capabilities, including its built-in API routes. This dual nature allows developers to build full-stack applications with unprecedented speed and efficiency. You can render user interfaces, manage server-side logic, interact with databases, and connect to external services, all within a single, cohesive framework. But this power comes with a critical responsibility. When you leverage Next.js API routes, you're not just building a front-end, you are exposing server-side endpoints to the internet. These routes can handle sensitive operations, process user input, and act as a crucial link to your backend systems. Without dedicated attention to their security, these convenient endpoints can unwittingly become the weakest link in your application's defenses. Many developers, accustomed to focusing purely on front-end concerns, might oversee the unique security challenges presented by Next.js's server-side capabilities. While Next.js itself is a secure framework, the way you architect and implement your API routes directly determines your application's overall security posture. Assuming that just because it's React it inherently has the same security profile as a static website is a dangerous misconception. This book is born from the undeniable imperative to secure these critical interfaces. It's designed to equip you, the Next.js developer, with the knowledge, strategies, and practical insights needed to build robust, bulletproof Next.js APIs. We will embark on a comprehensive journey, starting from the fundamental principles of authentication and authorization, and then progressively layering on more advanced security mechanisms. We'll demystify industry standards like OAuth and OpenID Connect, showing how they provide a secure framework for user access. You'll learn the intricacies of JSON Web Tokens, JWTs, their structure, their power, and their pitfalls, and discover why secure HTTP-only cookies are often their most reliable companion. We will delve into server-side session management using Redis, a lightning-fast data store that can enhance both security and scalability. Moving beyond authentication, we'll explore essential architectural patterns, such as the Backend-for-Frontend, BFF, proxy, demonstrating how Next.js API routes can act as a crucial security layer, safeguarding your core backend services. We'll confront crucial network-level defenses like cross-origin resource sharing, CORS, ensuring your browser-based applications can communicate securely across different domains. You'll also learn to implement content security policy, CSB, a powerful browser feature that acts as a frontline defense against various client-side injection attacks. Finally, we'll broaden our scope to discuss common API vulnerabilities beyond just access control, drawing insights from industry best practices. By the end of this book, you'll possess a holistic understanding of how these disparate security concepts intertwine, forming a multi-layered, defense-in-depth strategy that protects your Next.js application comprehensively. No prior specialized cybersecurity knowledge is assumed. This book will guide you step by step, explaining complex topics in clear, accessible language, using relatable analogies and practical examples to solidify your understanding. Our goal is not just to explain what to do, but to empower you with the why behind each security measure, enabling you to make informed architectural decisions and proactively build applications that are resilient to the threats of tomorrow. Let's begin the journey to building bulletproof Next.js APIs. Your users, your data, and your peace of mind depend on it. 2. Next.js API routes. The gateway to your backend. In the early days of the web, a user's browser would request an entire web page from a server. The page would arrive fully formed, like a letter already written. As web applications grew more complex and interactive, a new paradigm emerged. Instead of requesting whole pages, applications started fetching small, specific pieces of data or performing discrete actions without reloading the entire page. This shift led to the rise of what we now call APIs, Application Programming Interfaces. Next.js, as a modern framework designed for building sophisticated web applications, embraces this API-driven approach wholeheartedly. It provides a clever and convenient feature known as API routes. These are special files within your Next.js project that function as server-side endpoints, acting as gateways to your application's backend logic and data. Think of your Next.js application as a bustling town. The familiar pages you build for users, your homepage, your product listings, your contact forms, are like the public buildings. Next.js API routes, on the other hand, are like the town's special services entrance, tucked away for specific, authorized operations. While your users interact with the public buildings, their actions often trigger requests to these service entrances to fetch data, save information, or perform critical functions. What are Next.js API routes? At their core, Next.js API routes allow you to create API endpoints directly within your Next.js project, instead of setting up a separate backend server. Though we'll explore the benefits of doing so later, you can write server-side code that responds to HTTP requests right alongside your front-end code. The magic happens through a file system-based routing convention. If you create a file named, for instance, pages/API/users.js or app/API/users/route.js in newer Next.js versions, Next.js automatically creates an API endpoint accessible at /API/users. When a browser or another client sends a request to this URL, the code inside users.js or route.js springs into action on the server. This is a crucial distinction. Unlike your React components which execute in the user's browser, API routes run on the server, just like a traditional backend. Common use cases for API routes. With their server-side execution capability, Next.js API routes are incredibly versatile. Here are some typical scenarios where they shine. Data fetching and manipulation. This is perhaps the most common use. Your front-end component might need a list of products, the details of a specific user, or the results of a search query. An API route can query a database, process the results, and send back the necessary data to the front end. Similarly, when a user fills out a form, an API route can receive that data and save it to your database. Form submissions. Rather than directly exposing your database credentials to the client, a contact form submission can be sent to an API route. This route can then securely process the data, perhaps sending an email, logging the submission, or storing it in a database, all without exposing sensitive backend details. Proxying requests to external APIs. Imagine your front end needs to interact with a third-party service, like a payment gateway or a weather API. If that service requires an API key, you wouldn't want to embed that key directly in your client-side code, as it could be easily stolen by a malicious user. Instead, you can create a Next.js API route that acts as a secure intermediary. Your frontend calls your API route, and your API route, equipped with the hidden API key, then calls the external service. Your sensitive key never leaves your server. Handling sensitive business logic. Any operation that involves sensitive calculations, credentials, or interactions that should not be visible to the user's browser is a prime candidate for an API route. This could include processing a payment, generating a report, or triggering a secure backend process. The request-response cycle. When a client, typically a web browser, makes a request to a Next.js API route, that request is intercepted by the Next.js server. The server then executes the corresponding API route file, passing it two key objects. The request object, rec. This object contains all the information about the incoming request. This includes the HTTP method used, e.g., get, post, put, delete. Any data sent in the request body, important for post requests, like form submissions. Query parameters from the URL, e.g., ID equals 123. HTTP headers, like authorization headers, which we'll discuss extensively. Information about the client, e.g., its IP address. The response object, raise. This object allows your API route to construct and send a response back to the client. Using this object, you can send data back, e.g., JSON, text, or even files. Set HTTP status codes, e.g., 200 for success, 404 for not found, 401 for unauthorized, 500 for server error. Set HTTP headers, crucial for security attributes like cookies or CORS headers. Redirect the client to another URL. The API routes code processes the incoming request, rec, performs its necessary logic, e.g., fetching data, saving records, and then constructs an appropriate response, raise, to send back to the client. This elegant pattern allows for a clear separation of concerns, with the client handling the user interface and the API route handling the server-side operations. The initial security surface. Open doors. While incredibly convenient, the direct exposure of Next.js API routes to the internet introduces a significant security surface. Unlike client-side code, which is primarily concerned with user interaction and display, API routes are server-side resources that can directly access databases, interact with file systems, and communicate with other backend services. This makes them prime targets if not properly secured. Consider our town analogy again. The API routes are like the service entrance. If you leave this entrance unguarded, anyone can wander in. They might not know where to go initially, but a determined individual could, through trial and error, find sensitive areas or even steal valuable goods. Without any security measures in place, your API routes are vulnerable to unauthorized access. Anyone with an internet connection could theoretically send requests to your API routes. If these routes don't check who is making the request or what privileges they have, sensitive data could be exposed or critical actions could be performed by malicious actors. Information disclosure. Even if an API route isn't directly manipulative, poor design could inadvertently reveal crucial information about your system's inner workings, database structure, or connected services. Error messages that are too verbose, for example, can be a goldmine for attackers. Malicious input. Attackers can send malformed or malicious data to your API routes, attempting to exploit weaknesses like SQL injection, cross-site scripting, XSS, or buffer overflows, potentially leading to data corruption, unauthorized command execution, or service disruptions. Basic considerations for API route security. Before we dive into the advanced concepts of authentication, authorization, and network defenses, it's essential to grasp a few fundamental security principles that apply to any server-side endpoint, including Next.js API routes. Assume all input is malicious and validate it. Never trust data coming from the client. Always validate, sanitize, and ideally, transform user input before processing it or passing it to other systems, like a database. This means checking data types, lengths, formats, and ensuring it doesn't contain unexpected characters or commands. A missing input validation check is a classic entry point for many attacks. Filter and limit output. Just as you should filter input, you should also be careful about what data you send back in responses. Only return the necessary information to the client. Avoid exposing internal identifiers, sensitive database fields, or excessive error details that could aid an attacker in mapping out your system. Mind your secrets and environment variables. API keys, database credentials, and other sensitive configurations should never be hard-coded directly into your API root files or any part of your client-side code. Next.js provides excellent support for environment variables, which allow you to keep these secrets out of your source code and manage them securely during deployment. This is a foundational step in preventing credential exposure. Embrace the principle of least privilege. When your API route interacts with other services or databases, ensure it only has the minimum necessary permissions to perform its intended function. If a route only needs to read user profiles, it should not have permissions to delete them. These basic considerations form the groundwork. While critical, they are merely the starting point. The subsequent chapters will build upon this foundation, introducing sophisticated mechanisms to rigorously control who can access your API routes and what they are permitted to do, transforming your exposed gateways into truly secure portals. 3. Authentication fundamentals. Who are you? Before we dive into the complex world of OAuth, JWTs, and secure cookies, we need to establish a clear understanding of two fundamental pillars of application security: authentication and authorization. These terms are often used interchangeably in everyday conversation, but in the realm of cybersecurity, distinguishing between them is paramount. Misunderstanding their roles can lead to critical security vulnerabilities in your Next.js APIs. Authentication, authn, the act of proving identity. Imagine you're trying to enter a private club. At the door, a bouncer asks for your ID. You present your driver's license. The bouncer examines it, perhaps checks your photo, and then compares it to a list of registered members. If everything matches, they confirm, yes, this is indeed Sarah Smith, a registered member. This process is authentication. It's the act of verifying someone's or something's claimed identity. In the digital world, authentication is how an application confirms that a user is who they say they are. It answers the question, who are you? Authentication typically involves presenting credentials, pieces of information known only to the legitimate user or something they possess. Common types of credentials or authentication factors include something you know. This is the most common form, like a username and password, a personal identification number PIN, or a secret question and answer. Something you have. This includes physical tokens like security keys, e.g., a UBI key, smart cards, or even your mobile phone receiving a one-time code via SMS. Something you are. These are biometric factors, such as fingerprints, facial recognition, or iris scans. Modern security often combines these factors into multi-factor authentication, MFA. For instance, requiring a password, something you know, and a code from your phone, something you have, significantly enhances security, making it much harder for an unauthorized party to gain access even if they compromise one type of credential. Authorization, authc, the act of granting permission. Now, let's go back to our club analogy. Sarah Smith has successfully authenticated and is inside the club. She approaches a velvet rope leading to a VIP lounge. A second bouncer asks, "Are you permitted into the VIP area?" The bouncer checks a list. It turns out Sarah Smith is only a standard member, not a VIP. So, despite being authenticated to enter the club, she is not authorized to enter the VIP lounge. This is authorization. Once an identity has been verified, authenticated, authorization determines what specific actions that authenticated entity is permitted to perform or what resources they can access. It answers the question, what can you do? Or are you allowed to do this? Authorization often relies on roles. Users are assigned roles, e.g., administrator, editor, guest. Each role has a predefined set of permissions. Permissions, specific actions a user or role can perform, e.g., create post, delete user, view analytics. Policies, rules that define authorization logic, often based on attributes of the user, the resource, or the context of the request. Crucially, authorization always happens after authentication. You cannot determine what someone is allowed to do if you don't first know who they are. An anecdote to clarify. Consider a library. A person walks up to the front desk and asks to check out a book. Authentication. The librarian asks for their library card. The person presents it. The librarian scans the card and checks the system to confirm that the card number matches a valid, active member in their records. This confirms their identity as a valid library member. Authentication successful. Authorization, Scenario 1. The person then tries to check out a special, restricted research journal. The librarian checks the item's classification and the person's membership level. "I'm sorry," the librarian says, "that journal is only available to faculty members, and your membership is for general readers." Even though the person is a valid member, they are not authorized to access that specific item. Authorization, Scenario 2. A different person arrives, claiming to be Professor Jenkins, a known faculty member. They don't have their card, but say they left it at home. The librarian, perhaps unwisely, bypasses the card check based on their claim. The person then tries to access the faculty-only archives. The librarian, still thinking it's Professor Jenkins, grants access. Later, it turns out the person was an imposter. Here, failed authentication led to an incorrect authorization decision. This illustrates why clear, distinct authentication and authorization checks are vital for your Next.js API routes. An API route can confirm a user's identity, authentication, and then, based on that confirmed identity, enforce what actions that user is allowed to perform, authorization. Maintaining state, stateful Vs. Stateless authentication. Once a user has been authenticated, how does the application remember their identity for subsequent requests? This brings us to the concepts of stateful and stateless authentication. Stateful authentication, session-based. In stateful authentication, the server maintains a session for each authenticated user. When a user logs in, the server creates a unique session ID and stores it, along with user-specific data, in a server-side session store, e.g., in memory, a database, or a dedicated session server like Redis. This session ID is then sent to the client, usually as an HTTP-only cookie. With every subsequent request from the client, the session ID cookie is sent back to the server. The server uses this ID to look up the user's session data and verify their identity. Pros: easy revocation. Sessions can be instantly invalidated, e.g., when a user logs out or if their account is compromised, by deleting the server-side session record. This makes forced logout straightforward. Simple implementation. Concepts are generally simpler to grasp for beginners. Cons: scalability challenges. In distributed systems, multiple servers handling requests, managing shared session state can be complex. Each server needs access to the same session store, which can become a bottleneck. Server burden: the server has to store and manage sessions, which consumes memory and resources. Stateless authentication, token-based. In stateless authentication, the server does not maintain session data for each user. Instead, after a user authenticates, the server issues a self-contained token, commonly a JSON Web Token or JWT. This token contains all the necessary information about the authenticated user and their permissions. The server digitally signs this token using a secret key, ensuring its integrity and authenticity. The client stores this token, e.g., in an HTTP-only cookie or local storage, and sends it with every subsequent request. The server then verifies the token's signature, extracts the user's identity and permissions directly from the token, and proceeds with the request without needing to perform any server-side lookup. Pros: scalability. Since no session state is maintained on the server, any server instance can validate a token. This is ideal for distributed systems, microservices architectures, and serverless environments, like Next.js API routes running as serverless functions. Reduced server burden, less memory and processing power dedicated to session management. Cons: token revocation. Invalidating a token before its natural expiry is more complex without a server-side session store. This often requires additional mechanisms like blacklisting, which then reintroduces some state. Token exposure. If a token is compromised, it remains valid until it expires, potentially for a long time. Common authentication mechanisms, an overview. While the implementation details vary, most authentication mechanisms in web applications fall into one of these conceptual categories. Basic authentication, a very simple mechanism where credentials, username, and password are encoded and sent in the authorization header of every HTTP request. It's often used for simple APIs, but is generally insecure without HTTPS. API keys, a string of characters issued uniquely to a user or client application. The client includes this key in requests to authenticate. While useful for simple services or rate limiting, API keys are often static and difficult to revoke without reissuing a new key to all clients. They mostly authenticate the application, not the user. Session IDs, as described above, commonly used in traditional web applications for stateful authentication. Tokens, e.g., JWTs, as introduced for stateless authentication, becoming increasingly popular for modern APIs and single-page applications. In the upcoming chapters, we will deeply explore OAuth, OpenID Connect, and JSON Web Tokens as the cornerstone technologies for implementing secure and scalable authentication and authorization in your Next.js applications, addressing the nuances and best practices for each. Understanding the fundamental distinction between who you are and what you can do is the critical first step in building a truly secure system. 4. Deciphering OAuth 2.0 and OpenID Connect. Imagine you want to use a photo editing app to touch up pictures stored in your cloud photo album. In the past, this might have required you to give the photo editing app your cloud photo album username and password. This is incredibly risky. If the photo app were compromised, your main cloud account and everything else in it would be vulnerable. This scenario is precisely the problem that OAuth, Open Authorization, was designed to solve. OAuth 2.0 is not an authentication protocol itself, but rather an authorization framework. Its primary purpose is to allow a user to grant a third-party application limited access to their resources on another service without sharing their credentials. It facilitates delegated authorization. In essence, it answers the question, can this application act on my behalf to access these specific things from this other service? The problem OAuth solves, delegated authorization. Let's break down the core problem. You, the resource owner, have resources, like your photos, calendar, or contacts, stored on a resource server, like Google Photos, Microsoft Outlook, or Apple Contacts. You want to grant access to a client application, like that photo editor? How do you do this securely? Before OAuth, you'd have two bad options. Give the client your credentials. Highly insecure, as it grants the client full control, and if the client gets hacked, your credentials are stolen. Manually transfer data, cumbersome and impractical for dynamic applications. OAuth introduces a secure middle ground. Instead of giving the client your login details, you grant it an access token. This token is like a special, single-purpose key that the client can use to access only those resources you've approved, and only for a limited time. You give your approval, not your password. Key roles in OAuth 2.0. OAuth defines 4 fundamental roles that interact during the authorization process. Resource owner. This is the user who owns the protected resources, e.g., your photos on Google. You are the one granting permission. Client. The application that wants to access the protected resources on behalf of the user, e.g., the photo editing app. This can be a web application, a mobile app, or even a desktop application. Authorization server. The server that authenticates the resource owner and issues access tokens to the client after obtaining the resource owner's authorization, e.g., Google's authentication system. It confirms who you are and whether you agree to the access request. Resource server. The server hosting the protected resources, capable of accepting and responding to protected resource requests using access tokens, e.g., Google Photos API. How OAuth 2.0 works. The authorization code flow with PKCE. There are several grant types, or flows, in OAuth 2.0, each suited for different client types. For Next.js applications, which run in a web browser, a public client, because its code can be inspected, The most secure and recommended flow is the authorization code flow with proof key for code exchange, PKCE. Let's walk through a simplified version of this secure dance. Client requests authorization. The user, while using the client application, your Next.js app, clicks a button like Connect with Google. The client redirects the user's browser to the authorization server, e.g., accounts.google.com. This redirect includes parameters like cliented, identifies your Next.js application to the authorization server, redirectory, where the authorization server should send the user back after they've made their decision. Scope, a list of permissions the client is requesting, e.g., read, photos, write, calendar. Response type equals code, indicating that the client wants an authorization code. Code challenge and code challenge method. These are the PKCE parameters, used to prevent certain attack vectors, ensuring that only the original client application can exchange the code for tokens. Resource owner authenticates and authorizes. The authorization server authenticates the user, the resource owner. This is where you type in your Google username and password. After successful authentication, the authorization server presents a consent screen to the user, asking if they approve the client's requested permissions. The scope. Do you grant this photo app access to your photos? Authorization server issues authorization code. If the user approves, the authorization server redirects the user's browser back to the redirectory specified by the client, appending a short-lived authorization code and the code verifier, PKCE, in the URL. Client exchanges code for tokens. Crucially, this authorization code is transferred via the browser, but it cannot be directly used to access resources. The client, your Next.js app on the server side, perhaps leveraged via a Next.js API route serving as a Backend-for-Frontend, which we'll address in Chapter 8, now makes a direct, server-to-server request to the authorization server's token endpoint. This request includes the cliented and client secret, if the client is confidential, though for public clients, PKCE often replaces the need for a client secret in this exchange. The authorization code it just received. The redirectory to confirm it matches. The code verifier from PKCE to prove it's the same client that initiated the flow. Grant type equals authorization code. Authorization server issues tokens. If the authorization server validates the authorization code and the PKCE parameters, it issues the client an access token, a credential that represents the resource owner's delegated authorization to the client. This token is what the client will use to make requests to the resource server. Optionally, a refresh token, a long-lived token that allows the client to obtain new access tokens after the current one expires, without requiring the user to re-authenticate or reauthorize. If OpenID Connect is used, an ID token. We'll discuss this next. Client accesses protected resources. The client now uses the access token to make requests to the resource server, e.g., Google Photos API. The resource server validates the access token and, if valid, grants access to the requested resources. This flow is highly secure for public clients because the sensitive access and refresh tokens are never exposed in the browser's URL bar or easily intercepted. The authorization code is a one-time use credential, and the PKCE mechanism prevents an attacker from intercepting and reusing it. Tokens, access and refresh. Access token. This is the actual credential used by the client to access protected resources on the resource server. It's usually a short-lived, minutes to an hour JSON Web Token, JWT, which we'll cover in detail in Chapter 5. Its short lifespan limits the damage if it's compromised. Refresh token. These are typically long-lived, days to months, and are meant to be kept very secure, usually in an HTTP-only cookie. Because access tokens expire quickly, a refresh token allows the client to obtain a new access token from the authorization server without prompting the user to re-authenticate. This provides a smoother user experience while maintaining security. If a refresh token is compromised, it can be revoked by the authorization server. OpenID Connect. Adding an identity layer on top of OAuth 2.0. While OAuth 2.0 is about authorization, it doesn't standardize how to verify the user's identity. That's where OpenID Connect, OIDC, comes in. OIDC is a thin identity layer built on top of OAuth 2.0. It allows clients to verify the identity of the end user based on the authentication performed by an authorization server, as well as to obtain basic profile information about the end user. In simple terms, OAuth 2.0 equals authorization. Can this app access my photos on Google? OpenID Connect equals authentication plus authorization. Is this user genuinely John Doe from Google? And can this app access his photos? When OIDC is used, the authorization server, now also called an OpenID provider or OP, issues an additional token during the code exchange. ID token. This is a JSON Web Token, JWT, that contains claims information about the authenticated user, such as their unique identifier, name, email address, and authentication time. The ID token is cryptographically signed by the OpenID provider, allowing your client application to verify its authenticity and extract user information directly. It's truly about identity. OIDC is what powers the ubiquitous login with Google, sign in with Apple, or login with Facebook buttons you see on many websites. These services act as the OpenID provider, simplifying user authentication for your application. Benefits of using OAuth 2.0 and OpenID Connect. Enhanced security. Users never share their primary credentials with third-party applications. Limited, revocable tokens are used instead. User convenience. Single sign-on, SSO, capabilities mean users don't need to create and manage separate passwords for every service. Granular permissions. Users can grant specific limited access scopes to their resources rather than all-or-nothing access. Industry standard, widely adopted, well-documented, and supported by major service providers. Scalability. Especially for token-based flows, the identity verification relies on the secure OpenID provider rather than your application needing to manage user passwords. While integrating with an OAuth 2.0 and OpenID Connect provider might seem complex at first glance due to the many moving parts, the immense security and usability benefits it provides make it an indispensable part of modern web application architecture. In coming chapters, we'll see how Next.js API routes play a crucial role in orchestrating this flow, especially when acting as the secure intermediary, the BFF, between your front end and these external authentication services. Understanding these protocols is the gateway to securely identifying your users and managing their access. 5 JSON Web Tokens, JWT, the stateless credentials. In the previous chapter, we explored OAuth 2.0 and OpenID Connect, the protocols that orchestrate how an application requests and obtains permission to access resources, and how a user's identity is verified. At the heart of these modern authentication and authorization flows lies a seemingly simple yet incredibly powerful data format, the JSON Web Token, or JWT, pronounced JWT. When an authorization server, like Google or Auth0, issues an access token or an ID token, it's very often in the form of a JWT. These tokens are compact, URL-safe, and self-contained, designed to transmit information securely between parties. They represent a fundamental shift towards stateless authentication, allowing a server to verify a user's identity and rights without needing to consult a database for every single request. Think of a JWT as a special kind of digital boarding pass or a VIP badge. Once issued, this pass contains all the necessary signed information about you, who you are, when it was issued, and how long it's valid for, so that various checkpoints can verify your access without needing to call the airline headquarters or club management every time. The structure of a JWT. A JWT typically consists of 3 parts, separated by dots, much like sections in a serialized string. Header payload signature. Let's break down each component. 1. The header. The header is a JSON object that typically contains 2 pieces of information. Algorithm. This specifies the cryptographic algorithm used to sign the JWT. Common algorithms include HMAC with SHA-256, HS-256, for symmetric key signing, or RSA with SHA-256, RS-256, for asymmetric key signing. Type. This indicates that the token is a JWT. Example encoded conceptually, ALG HS256, type JWT. This header is then base 64 URL, encoded to form the first part of the JWT string. It's like the label on a sealed package, telling you how the package was sealed and what kind of package it is. 2. The payload. The payload is another JSON object that contains the claims. Claims are statements about an entity, typically the user and additional data. There are 3 types of claims. Registered claims. These are a set of predefined, non-mandatory claims recommended for common use cases. They include issuer, identifies the entity that issued the JWT. Subject, identifies the principal user that the JWT is about. Audience, identifies the recipients that the JWT is intended for. Expiration time, the time after which the JWT must not be accepted for processing, crucially important for security. Issued at, the time at which the JWT was issued. NBF, not before, the time before which the JWT must not be accepted for processing. JWT ID, a unique identifier for the JWT, useful for preventing replay attacks. Public claims. These are custom claims defined by parties using JWTs. To avoid collisions, they should be defined in the IANA JSON Web Token registry or be a URI that contains a collision-resistant namespace. Private claims. These are custom claims created to share information between specific parties who agree on their meaning. They are not registered or publicly defined. Example, encoded conceptually. User 123, name, John Doe, admin, false, exp. 1,678,886,400, where exp is a Unix timestamp. The payload is also base 64 URL, encoded to form the second part of the JWT string. It's crucial to understand that base 64 URL encoding is not encryption. It's merely a way to represent binary data in an ASCII string format. Anyone can decode the header and payload of a JWT to read its contents. Therefore, you should never put sensitive, confidential information directly into the JWT payload, unless the entire JWT is encrypted, which is a separate topic, called JWE, JSON Web Encryption, and is less common for access tokens. 3. The signature. The signature is the cryptographic component that gives the JWT its security properties. It ensures that the token has not been tampered with and that it was indeed created by the expected sender. The signature is created by taking the base 64 URL encoded header, the base 64 URL encoded payload, a secret key for symmetric algorithms like HS256, or a private key for asymmetric algorithms like RS256, and applying the algorithms specified in the header. Signature equals algorithm, base 64 URL encode header plus base 64 URL encode payload secret. This signature is appended as the third part of the JWT. When your Next.js API route receives a JWT, it performs the reverse process. It decodes the header and payload, then recalculates the signature using the same algorithm and the same secret key or public key if asymmetric. If the calculated signature matches the signature attached to the token, the API route can be confident that integrity, the token's content, header, and payload, has not been altered since it was signed. Authenticity, the token was signed by someone who possesses the original secret key or private key, which should only be the legitimate issuer, your authorization server. This verification happens with every request, immediately establishing trust in the token's claims without needing to ask the original issuer again. The power of statelessness, the primary advantage of JWTs, particularly for microservices and scalable architectures, is their statelessness. Because the token itself contains all the necessary information and its integrity is verifiable through the signature, the server doesn't need to store any session information. Consider our boarding pass analogy again. Once you have a valid boarding pass with your name, flight details, and a security check stamp, airport staff can let you through various checkpoints simply by scanning your pass. They don't need to constantly call a central database to confirm your identity for every gate, security check, or boarding zone. The pass itself is proof. This stateless nature means scalability. Any server instance can validate a JWT independently. You can add more Next.js API root instances or backend services without worrying about sharing session state across them. This is especially beneficial in cloud environments where instances can be dynamically added or removed. Reduced server load. No need to query a database or cache for session data on every request, reducing I/O operations. Interoperability. JWTs are an open standard, making them easy to use across different services and languages. JWT vulnerabilities and mitigation strategies. While powerful, JWTs are not a silver bullet. They come with their own set of security considerations. One, lack of immediate revocation. This is the biggest challenge with stateless tokens. Once a JWT is issued, it's typically valid until its expiration time is reached. If a user logs out, changes their password, or their token is compromised, a stateless JWT might still be accepted by the API until it naturally expires. This means that if an attacker steals an active JWT, they can use it for the remainder of its valid lifetime. Mitigation. Short-lived access tokens plus secure refresh tokens. The most common solution is to issue access tokens with a very short lifespan, e.g., 5 to 15 minutes. When an access token expires, the client uses a separate, long-lived refresh token to obtain a new access token from the authorization server. Refresh tokens should be stored very securely, preferably in HTTP-only cookies discussed in Chapter 6, and they can be revoked by the authorization server at any time. If a user logs out or their password changes, only the longer-lived refresh token needs to be invalidated. Mitigation. Server-side blacklisting invalidation. For critical scenarios where immediate revocation is essential, e.g., a security incident, forced logout, a server-side store, like Redis, which we'll explore in Chapter 6, can be used to maintain a blacklist or denalist of invalidated JWTs. When an API receives a JWT, it first checks if the token's unique ID, JTI claim, is on the blacklist before validating its signature. This reintroduces a small amount of state, but provides necessary revocation capabilities. 2. Signature forgery or bypass. Early JWT implementations sometimes had vulnerabilities in how they handled signature algorithms, e.g., allowing none, where no signature verification was performed. Robust JWT libraries and careful configuration have largely mitigated these specific attacks, but it underscores the importance of using strong, random secrets keys. The secret used to sign JWTs for symmetric algorithms, or the private key for asymmetric algorithms, must be kept absolutely confidential and be sufficiently complex. If an attacker can guess or obtain this key, they can forge valid JWTs. Always verify the signature. Every Next.js API root receiving a JWT must verify its signature using the correct secret public key. Invalid signatures should be immediately rejected. 3. Insecure claims/data exposure. As mentioned, the JWT payload is only encoded, not encrypted. If you put sensitive personal identifying information, PII like full names, addresses, or social security numbers directly into the JWT payload, it will be visible to anyone who intercepts the token. Mitigation. Only include non-sensitive, necessary data in the JWT payload, e.g., user ID, roles, permissions. Any truly sensitive data should be retrieved from a secure backend service, e.g., a database, using the user ID from the validated *JWT. 4. Token theft via cross-site scripting XSS. If a JWT is stored in a client-side mechanism like local storage or session storage, it can be vulnerable to cross-site scripting XSS attacks. An XSS vulnerability allows an attacker to inject and execute malicious client-side scripts in a user's browser, which could then steal the token from the user's browser storage. Once stolen, the token can be used to impersonate the user. Mitigation. the safest place to store access tokens, and especially refresh tokens, for web applications is in HTTP-only and secure cookies. We will dive deep into why and how to use these special types of cookies in the next chapter. These attributes prevent JavaScript from accessing the cookie, making it immune to typical XSS token theft. Best practices for JWT implementation. To build truly secure Next.js APIs with JWTs, adhere to these key principles. Store tokens securely. Prioritize HTTP-only, secure, and same site equals lax or strict cookies for storing JWTs, especially refresh tokens. Keep access tokens short-lived. Minimize the window of opportunity for stolen tokens to be exploited. Implement refresh token rotation. After issuing a new access token using a refresh token, invalidate the old refresh token and issue a new one. This limits the damage if a refresh token is compromised. Validate all claims. Beyond just the signature, your API routes must validate the EXP, NBF, AUD, IS claims to ensure the token is still valid, intended for your application, and came from the correct issuer. Never put sensitive data in payload. Unless the entire JWT is encrypted, JWE, keep sensitive PII server-side. Use strong secret keys, asymmetric keys. Protect your signing keys with extreme care. Consider using dedicated secret management services for production environments. Implement token revocation, blacklisting for critical events. For user logout, password changes, or security incidents, ensure immediate invalidation. Regular auditing and monitoring. Keep an eye on your authentication system for unusual patterns or failed authentication attempts. JWTs are a cornerstone of modern, scalable API security. By understanding their structure, benefits, and common pitfalls, and by applying these best practices, you can leverage their power to build incredibly robust and secure Next.js API routes, ensuring that only authenticated and authorized users can access your valuable resources. Our next step is to explore the intricacies of secure session management, focusing on how HTTP-only cookies and external stores like Redis play a critical role in managing these powerful tokens. 6. Secure session management, cookies, Redis, and beyond. In the previous 2 chapters, we explored the concepts of authentication and authorization, and then delved into JSON Web Tokens, JWTs, as a powerful mechanism for stateless credentials. Now, an important question arises. How do we securely manage these credentials and maintain a user's logged-in state across multiple requests without sacrificing security or scalability? This is the domain of session management. Whether you're using traditional session IDs or modern JWTs, the way you handle persistent state between user and server is paramount to security. The browser's primary tool for maintaining state is the HTTP cookie. And when combined with a robust server-side store like Redis, it forms a highly secure and performant session management system. The role of cookies in web sessions. Cookies are small pieces of data that a server sends to a user's web browser, which the browser then stores. When the browser makes subsequent requests to the same server or domain, it sends those cookies back. This seemingly simple mechanism is what allows websites to remember you, keep you logged in, or recall your preferences. In the context of authentication, cookies typically transport session identifiers or authentication tokens, like JWTs, from the client to the server with each request. This means your Next.js API route can always identify the user making the request. However, not all cookies are created equal, especially from a security standpoint. Merely sending a token in a cookie is insufficient. Securing that cookie is vital to preventing common web vulnerabilities. Cookie security attributes, fortifying your digital handshake. To transform a regular cookie into a secure one, specific attributes must be set. These attributes instruct the browser on how to handle the cookie, significantly minimizing the risk of various attacks. HTTP only. Purpose. This is arguably the most critical security attribute for cookies containing sensitive information like session IDs or JWTs. When HTTP only is set, the cookie becomes inaccessible to client-side scripts, e.g., JavaScript code running in the browser. Why it's crucial? Without HTTP only, if an attacker manages to inject malicious JavaScript into your web page, a cross-site scripting XSS attack, they could easily read your user's authentication cookies and steal their session. With HTTP only, even if XSS occurs, the attacker cannot access the cookie's content, effectively preventing session hijacking. Impact on Next.js. For authentication tokens or session IDs, they must be stored in HTTP-only cookies. If you're using JWTs, this means the access token, or, more commonly, the refresh token if short-lived access tokens are used directly, should reside in an HTTP-only cookie. This is why storing JWTs in local storage is generally discouraged for actual authentication, as local storage data is fully accessible via JavaScript and vulnerable to XSS. Secure. Purpose. When this attribute is set, the cookie will only be sent over encrypted HTTPS connections. Why it's crucial. Without secure, your cookies could be transmitted over unencrypted HTTP. An attacker performing a man-in-the-middle (MITM) attack on an unsecured network could easily intercept the cookie and steal the user's session. Always use HTTPS in production. Same site, purpose. This attribute provides protection against cross-site request forgery (CSRF) attacks. It tells the browser whether to send the cookie when a request originates from a different site. Modes. Same site equals lax, recommended default for many use cases. Cookies are sent with top-level navigations, e.g., when clicking a link to your site from another site, and with GET requests initiated by third-party websites. They are not sent with cross-site post requests. This offers a good balance of security and usability. Same site equals strict, most secure. Cookies are only sent when the request originates from the same site. This provides the strongest protection against CSRF, but can sometimes break legitimate cross-site functionality, e.g., a user clicking a payment link from another banking site. Same site equals none, least secure for CSRF, requires secure. Cookies will be sent with all same site and cross-site requests. This is primarily used for cross-site functionality, where cookies are absolutely necessary, e.g., embedding content from your domain on another site, but it must be paired with the secure attribute and robust CSRF tokens. Why it's crucial. A CSRF attack tricks a user into unknowingly making an authenticated request to an application where they are already logged in. For instance, if you're logged into your banking website and tricked into clicking a malicious link on another site, a CSRF attack could potentially transfer money from your account. Same-site cookies significantly mitigate this risk. Domain and path. Purpose. These attributes control which URLs the cookie will be sent to. Why it's crucial. Domain limits the cookie to a specific domain, e.g., yourdomain.com. Path limits it to a specific subpath within that domain, e.g., /API. Setting these correctly prevents your cookies from being sent to unintended subdomains or paths, reducing the attack surface. Expires or max age. Purpose. Defines the lifespan of the cookie. Without these, a cookie is a session cookie and is deleted when the browser closes. Why it's crucial. For JWTs, this should align with the token's expiration. For refresh tokens, it should be a longer duration. Short-lived cookies for access tokens are preferable. Example for a Next.js API route. While we won't show code blocks, conceptually, an API route might set a secure cookie following a successful authentication like this. Response set header set cookie. Refresh token equals your refresh token, path equals / HTTP only, secure, same site equals lax, max age equals 36,000. Client-side storage, local storage versus secure cookies. A common dilemma for developers using JWTs is where to store them on the client side. Options include local storage, session storage, or cookies. Local storage and session storage. Pros. Easy to use, accessible directly via JavaScript, persistent across browser sessions. For local storage, larger storage capacity. Cons. Highly vulnerable to XSS. If an attacker can inject malicious JavaScript into your site, they can easily read everything in local storage or session storage, including your precious authentication tokens. This is a primary reason why storing actual access tokens or refresh tokens, There for authentication purposes is generally considered an anti-pattern. Secure HTTP-only cookies. Pros: resistant to XSS. Because of the HTTP-only flag, JavaScript cannot access their contents. The browser automatically sends them with requests. Resistant to CSRF. The same site attribute provides significant protection. Automatic. The browser handles sending and receiving the cookie. Cons: limited size. Cookies have a size limit around 4 KB. Sent with every request can slightly increase request payload size, though usually negligible for tokens. CSRF still possible with same site equals none. Requires careful handling. Conclusion on storage. For sensitive authentication tokens, like refresh tokens or even short-lived access tokens, secure HTTP-only cookies are nearly always the recommended choice for web applications. They offer a critical layer of defense against very common and dangerous attacks. Server-side session management with Redis. While secure cookies handle the transfer of session identifiers, the core data backing those identifiers often resides on the server. This is where a centralized, high-performance session store becomes invaluable. Redis Remote Dictionary Server is an excellent choice for this. What is Redis? Redis is an open-source, in-memory data structure store used as a database, cache, and message broker. Its key characteristics relevant to session management are, in memory, extremely fast read and write operations because data is stored in RAM. Key value store, simple, efficient storage and retrieval of data. Persistence, can be configured to persist data to disk, preventing data loss on restart. Versatile data structures, support strings, hashes, lists, sets, sorted sets, and more, making it flexible for various session-related data. How Redis powers secure sessions. Redis can play two crucial roles in secure session management for Next.js APIs. For traditional stateful sessions, when a user logs in, your Next.js API root generates a unique, cryptographically strong session ID. This session ID is used as a key in Redis, and the associated value is a JSON object containing user data, e.g., user ID, roles, last activity timestamp. The session ID is then set in an HTTP-only, secure, same-site cookie on the user's browser. On subsequent requests, the API root receives the session ID cookie, uses it to look up the session data in Redis, and authorizes the user. Benefit: enables easy, immediate session invalidation. To log a user out or revoke their session, simply delete their session ID from Redis. This centralized control is powerful for managing user access and security incidents. For JWT blacklisting invalidation, stateless tokens needing revocation. As discussed in Chapter 5, stateless JWTs are hard to revoke immediately. Redis provides an elegant solution. If a user logs out, changes their password, or if a token is compromised and needs immediate invalidation, your Next.js API root can add the unique ID, JTI claim of that JWT to a blacklist or denalist in Redis. When an API root receives a JWT, after verifying its signature, its first critical check is to see if the JTI of that token exists in the Redis blacklist. If it does, the token is rejected, effectively revoking it. Benefit: provides immediate revocation capability for long-lived refresh tokens or short-lived access tokens that need to be invalidated prematurely. Redis's fast lookup speed makes this check highly efficient. You can also set time-to-live TTL on blacklist entries to automatically expire them once the original JWT would have expired, preventing the blacklist from growing indefinitely. Advantages of using Redis for session data. Performance: being in memory, Redis offers blazing fast session data retrieval, crucial for high-traffic APIs. Scalability: it can be used as a centralized session store across multiple Next.js API root instances or even different backend services, ensuring consistency regardless of which server handles a request. Flexibility: can store various types of session data, whether full user objects or just token IDs. Reliability: with persistence options, session data can survive server restarts. Beyond cookies and Redis. Advanced session practices. While HTTP-only cookies and Redis form a strong foundation, secure session management involves ongoing vigilance. Session expiry. Always set reasonable expiration times for sessions. Short-lived sessions reduce the window for attack if a session is compromised. Session sliding. Extend a session's lifetime only upon active user interaction, rather than periodically. This helps prevent sessions from remaining active indefinitely in the background. Session regeneration. After a user successfully authenticates, logs in, or elevates their privileges, e.g., enters a password for a sensitive action, regenerate their session ID. This prevents session fixation attacks, where an attacker tricks a user into using a session ID that the attacker already knows. User logout. Provide clear and functional logout mechanisms that invalidate the session on both the client by deleting the cookie and the server by removing the session from Redis or adding the JWT ID to a blacklist. Monitor session activity. Keep an eye on unusual session patterns, such as multiple concurrent sessions from different IP addresses for the same user or sessions originating from suspicious locations. By combining the robustness of properly configured HTTP cookies with the speed and reliability of Redis for server-side state, you can build a highly secure and performant session management layer for your Next.js APIs. This provides the necessary foundation for managing authenticated users and preparing for more complex architectural patterns, such as abstracting your backend logic behind a dedicated API. 7. Microservices and dedicated backends. Scaling security. Up until now, we've primarily focused on securing individual Next.js API routes and the concepts and mechanisms vital for their internal security. Next.js offers incredible flexibility, blurring the lines between front-end and backend with these built-in API routes. For smaller applications or prototypes, using Next.js API routes directly for all your backend operations might be perfectly sufficient. However, as applications grow in complexity, scale, and the sheer volume of sensitive operations, a crucial architectural decision emerges. Should your Next.js API routes directly handle all business logic, database interactions, and integrations with external services? Or is it more secure and scalable to introduce a dedicated backend API service, separate from your Next.js application, which then manages communication with various deeper backend systems? This chapter explores the reasons why many large-scale, security-conscious applications opt for this separation, moving towards an architecture that might involve microservices or at least a distinct, hardened backend layer. Architectural styles. From monolith to microservices, historically, many applications were built as monoliths. This meant a single, large code base encompassed all functionalities front-end, backend logic, database access, and third-party integrations deployed as one giant unit. While seemingly simple to develop initially, monoliths can become unwieldy, difficult to scale parts independently, and challenging to update without affecting the entire system. The desire for greater agility, scalability, and independent deployment led to the rise of microservices. In a microservices architecture, an application is broken down into a collection of small, independent services. Each service typically focuses on a single business capability, operates in its own process, and communicates with other services through well-defined APIs. A dedicated backend API, while not necessarily a full microservices architecture, shares similar principles of separation of concerns. It means establishing a distinct, robust server application, which could be built with Node.js, Python, Java, Go, or any other suitable technology, whose sole responsibility is to house your core business logic, interact with databases, and connect to other critical internal or external systems. Why separate concerns? The case for a dedicated backend. The decision to introduce a dedicated backend, distinct from your Next.js frontend and its API routes, is often driven by a combination of factors, with security being a primary motivator. 1. Enhanced security and reduced attack surface. Principle of least privilege. By separating a dedicated backend, your Next.js application only needs the minimum necessary permissions to perform its duties. It communicates with the dedicated backend through a well-defined API, and the Next.js API routes can act as a proxy or Backend-for-Frontend, BFF, which we'll discuss in Chapter 8. This means the Next.js application itself does not need direct access to sensitive resources like the main production database, internal microservices, or confidential API keys for critical third-party services, e.g., payment gateways, external data providers. The surface area for attack from the internet directly on your most critical assets is significantly reduced. Centralized security enforcement, complex authorization logic, data validation, and sensitive business rules, e.g., users can only purchase X amount. Only admins can modify Y record, can be rigorously enforced within the dedicated backend. This layer becomes the single source of truth for these rules. If an attacker bypasses a front-end check, the dedicated backend still provides robust protection. Protection of internal networks. The dedicated backend can reside in a more protected part of your infrastructure, e.g., a private subnet within a cloud provider, with stricter firewall rules. Your Next.js application might be more exposed, but it acts as a controlled gateway, reducing the risk of a direct breach into your core systems. Specialized hardening. A dedicated backend can be hardened and secured using industry-specific best practices for server-side applications, often with a greater focus on deep security configurations, auditing, and threat detection that might not be practical or relevant for a Next.js environment. 2. Improved scalability. Independent scaling. Your front-end and backend often have different scaling requirements. Your Next.js application might need to scale horizontally to handle many concurrent users for content delivery, while your dedicated backend scales based on transaction volume or complex data processing. Separating them allows you to scale each component independently, optimizing resource utilization and cost. Load balancing. A dedicated backend can more easily be placed behind load balancers and robust API gateways that manage traffic distribution, rate limiting, and other network-level concerns, further isolating it from direct internet exposure. 3. Technology stack flexibility. Best tool for the job. You might prefer to build your high-performance, data-intensive backend in a language or framework different from JavaScript/Next.js, e.g., Python for machine learning applications, Java for enterprise systems, Go for high concurrency services. A separate backend allows this flexibility. Service evolution. Different teams can work on different services without stepping on each other's toes, allowing for faster development cycles and easier upgrades of individual components. 4. Clearer separation of responsibilities. Team specialization. Front-end teams can focus on user experience and the UI, while backend teams concentrate on data integrity, business logic, and system integrations. This often leads to more efficient development and higher quality code. Easier maintenance. Smaller, focused services are generally easier to understand, debug, and maintain than large, monolithic codebases. What belongs in the dedicated backend? Deciding what functionality to offload to a dedicated backend versus keeping within Next.js API routes requires careful consideration. Generally, the dedicated backend should handle core business logic, complex algorithms, financial calculations, order fulfillment, subscription management, etc. Sensitive data operations, direct interactions with your primary production database, reading, writing, updating, deleting sensitive user data, file storage for sensitive documents, critical third-party integrations, payment gateway APIs, SMS email services with high-value API keys, background processing queues. Your Next.js API route can proxy these, but the direct credentials and complex interactions should reside in the dedicated backend. Comprehensive authorization. While Next.js API routes can perform initial authorization checks, e.g., is this user authenticated? The dedicated backend is where granular, multi-layered authorization policies, e.g., can this manager approve this specific type of transaction, are typically enforced directly before data access or critical operations. Long-running processes, operations that might take a significant amount of time, batch processing, or complex data transformations. How the dedicated backend handles security. The dedicated backend itself must be secured rigorously. It will be responsible for validating access tokens. It receives JWTs or other authentication tokens from the Next.js application, or directly from clients if the architecture bypasses the Next.js BFF for some reason, and it must perform the full validation of these tokens, including signature verification, expiry checks, and claim validation, implementing granular authorization. Based on the claims within the validated tokens, the dedicated backend determines if the authenticated user has the necessary permissions to perform the requested action on the requested resource. This is where roles, permissions, and policy engines truly come into play. Secret management. Securely storing API keys, database credentials, encryption keys, and other sensitive configurations, perhaps using dedicated secret management services like AWS Secrets Manager, HashiCorp Vault, or Azure Key Vault. Input validation and output sanitization. Continuous, rigorous validation of all incoming data and meticulous sanitization of all outgoing data to prevent injection attacks and information disclosure. Rate limiting and throttling. Protecting itself against abuse by limiting the number of requests clients can make in a given period. Comprehensive logging and monitoring. To detect and respond to suspicious activity, errors, and security incidents. Next.js API routes as a thin layer. When you opt for a dedicated backend, your Next.js API routes often transition into a thin layer. Their primary roles become authentication and session management, handling the initial login flow, e.g., via OAuth OIDC, issuing and managing secure cookies for session or refresh tokens, proxying requests to the dedicated backend, acting as an intermediary, receiving requests from the front end, adding necessary authentication headers, and forwarding them to the dedicated backend. Basic front-end specific logic. Any logic that is purely for the benefit of the front-end UI and does not involve core business rules or sensitive data. Error handling and transformation. Translating errors from the dedicated backend into user-friendly messages for the front end. This lean approach minimizes the complexity and security surface area of your Next.js API routes themselves, allowing them to excel at their primary role of serving the front end effectively, while delegating the heavy lifting and critical security enforcement to the more robust and isolated dedicated backend. The concept of utilizing Next.js API routes in this intermediary role is known as the Backend-for-Frontend (BFF) pattern, which is the subject of our next chapter. By understanding this separation, you pave the way for building truly scalable, maintainable, and secure applications. 8. The Next.js API BFF, your secure gateway to the backend. In the previous chapter, we made a strong case for separating your core business logic and sensitive data interactions into a dedicated backend API. This architectural pattern significantly enhances security and scalability. Now, the question becomes, how does your Next.js frontend, and specifically its API routes, interact securely and efficiently with this separate backend? The answer often lies in implementing a Backend-for-Frontend (BFF) pattern. The BFF pattern dictates that for each distinct type of client application, e.g., a web application, an iOS mobile app, an Android mobile app, there should be a dedicated backend service tailored specifically for its needs. In our case, the Next.js API routes are perfectly positioned to embody this BFF layer for your web application. They act as a secure, specialized gateway, sitting between your Next.js client-side frontend and your powerful, potentially complex dedicated backend services. What is the Backend-for-Frontend (BFF) pattern? Imagine your primary backend is a grand, multi-purpose superstore. It has everything: groceries, electronics, clothing, a pharmacy. It serves everyone. Your Next.js frontend, however, might only need a specific set of items, say, just groceries and a few common household goods, arranged very conveniently for a quick pickup. A traditional frontend might have to navigate the entire superstore's complex layout, find each item, and then bring it back. A BFF, on the other hand, is like a personal shopper specifically for your Next.js app. It knows exactly what your app needs, goes into the superstore, collects only those items, perhaps even repackages them nicely, and brings them back to your app in an optimized format. It acts as a specialized API layer that serves the frontend's specific UI/UX requirements, preventing the frontend from needing to know the complexities of the underlying backend services. Why Next.js API routes as your BFF? Next.js API routes are an ideal candidate for implementing the BFF pattern for several compelling reasons. Server-side execution. As we've established, API routes run on the server. This is crucial because it allows them to perform operations that cannot be done securely or efficiently on the client side. Part of the same project. They live within your Next.js project, meaning they share the same tooling, development environment, and deployment pipeline as your front end. This simplifies development and maintenance. Client-specific logic. They can be tailored to the exact data needs of your Next.js frontend, transforming responses from the dedicated backend to fit the UI, reducing overfetching or underfetching. Security benefits of the Next.js API BFF. The BFF pattern, particularly when implemented with Next.js API routes, offers substantial security advantages. Hiding API secrets never expose credentials. The problem? Your dedicated backend or third-party services, like payment processors, AI APIs, SMS gateways, often require API keys, client secrets, or other sensitive credentials for access. If your frontend tries to call these services directly, these secrets would have to be embedded in your client-side JavaScript, making them easily discoverable and stealable by anyone inspecting your browser's network traffic or source code. The BFF solution, your Next.js API route, the BFF, acts as the intermediary. The frontend calls the BFF. The BFF, running on the server, makes the call to your sensitive backend service using the securely stored API key. The key never leaves your server-side environment. This is a critical defense against credential exposure, preventing direct backend access, controlled entry point. The problem: if your dedicated backend API is directly exposed to the internet, it becomes a wide-open target. Attackers can probe it, attempt to bypass access controls, or exploit vulnerabilities without needing to interact with your frontend at all. The BFF solution. The frontend only communicates with the Next.js API BFF. The dedicated backend can then be isolated, potentially residing in a private network or with very strict firewall rules, only allowing incoming connections from the BFF. This creates a secure moat around your most sensitive data and logic, significantly reducing the backend's attack surface. Simplifying authentication and token management. The problem: managing complex OAuth OIDC flows, refreshing expired access tokens, and securing refresh tokens can be challenging for a pure client-side application. Placing tokens directly in local storage is insecure, and cookies require careful handling. The BFF solution. The BFF handles all the complexities of token management. When your frontend needs authenticated data, it sends its secure HTTP only refresh token or session cookie to the BFF. The BFF validates this token cookie, and if needed, uses the refresh token to obtain a new, short-lived access token from the authorization server. This access token is then used to call the dedicated backend. The access token, which is typically a JWT, never needs to be sent to the client side. The BFF can even perform token validation on the edge before ever forwarding anything to the dedicated backend. This keeps the client-side code lean and clean from auth logic and immensely improves security by hiding tokens from JavaScript. Enforcing server-side authorization. The problem: relying solely on client-side authorization logic is a massive security flaw. Users can simply modify front-end code or parameters to bypass checks. The BFF solution. While the ultimate authorization decisions reside in your dedicated backend, the BFF can perform initial authorization checks based on the user's role or scope, potentially rejecting unauthorized requests before they even reach the core backend. This acts as an early filter and adds a defense-in-depth layer. Cross-origin isolation and CORS handling. The problem: if your frontend, e.g. app.example.com, directly calls your dedicated backend, api.example.com, you'll encounter cross-origin resource sharing, CORS issues, which we'll explore fully in Chapter 9. This requires careful CORS configuration on your dedicated backend. The BFF solution. Since the Next.js frontend calls its own origin for its API roots, e.g., app.example.com/API/proxy-data, there are no CORS restrictions between the frontend and the BFF. Any CORS complexities are then contained within the server-to-server call between the BFF and the dedicated backend, where CORS policies are much easier to manage and often less restrictive or even non-existent within a private network. Implementing the BFF with Next.js API roots, conceptual flow. Let's trace a typical authenticated data request with a Next.js API BFF. User logs in. User interacts with the Next.js frontend, authenticating via an OAuth OIDC flow, e.g., login with Google. Auth call to BFF. The frontend makes a post request to a Next.js API root, e.g., /API/auth/callback with the authorization code. BFF exchanges code for tokens. This API root, BFF, makes a server-to-server call to the authorization server's token endpoint to exchange the authorization code for access and refresh tokens. BFF secures refresh token. The BFF sets the refresh token, and potentially a very short-lived access token, though often just the refresh token is sufficient on the client side, in a secure HTTP-only, secure, same-site cookie, which is sent back to the user's browser. Front-end authenticated request. Later, the user's front-end needs to fetch some protected data, e.g., profile data. Instead of calling the dedicated backend directly, it makes a GET request to a Next.js API root, say /API/user/profile. The browser automatically attaches the secure HTTP-only cookie. BFF validates refreshes token. The /API/user/profile BFF root receives the request. It extracts the refresh token from the HTTP-only cookie. If the access token it previously held is expired, it uses the refresh token and its own client credentials to silently obtain a new access token from the authorization server or from its own token cache, then issues a new HTTP-only cookie for the refresh token. It critically checks if the refresh token is valid and not blacklisted, as discussed in Chapter 6. BFF proxies to dedicated backend. Now armed with a fresh access token, the BFF makes a server-to-server request to the dedicated backend API, e.g., https://backend.com/user/profile, including the access token in the authorization header. Dedicated backend responds. The dedicated backend validates the access token, performs the necessary authorization checks, fetches the data, e.g., from a database, and sends it back to the BFF. BFF transforms and responds to frontend. The BFF receives the data, may transform it into a format more suitable for the frontend, and then sends it back to the Next.js client. Throughout this entire process, sensitive credentials, like your backend's API keys or users' long-lived refresh tokens, are never directly exposed to the client-side JavaScript. The core backend is shielded from direct internet access, and authentication complexities are managed in a secure server-side environment. This layered approach significantly hardens your application against common web attacks. The Next.js API BFF is more than just a proxy. It's a strategic security control point that streamlines front-end development while fortifying your entire application architecture. In our next 2 chapters, we'll dive into 2 critical network-level security mechanisms that complement this architecture. CORS, which controls cross-origin interactions, and CSB, which locks down your front-end's content execution. 9. CORS, navigating cross-origin requests safely. Congratulations! You've built a robust Next.js application, fortified its API roots as a Backend-for-Frontend, BFF, implemented secure authentication, and even integrated a dedicated backend for your core business logic. Now, your brilliant frontend needs to talk to the BFF, and the BFF needs to talk to the dedicated backend. What could possibly go wrong at this stage? Enter cross-origin resource sharing, CORS. A mechanism designed to save you from dangerous security vulnerabilities, but often presenting itself as a mysterious, frustrating roadblock for developers. Understanding CORS is crucial because it's a fundamental security feature enforced by web browsers that dictates how web page content from one origin can request and interact with resources from another origin. The same origin policy, SOP, the guard dog of the browser. To understand CORS, we must first understand the same origin policy, SOP. Think of the SOP as a vigilant guard dog within your web browser. Its primary job is to prevent malicious scripts from one website from accessing sensitive data or performing unauthorized actions on another website. An origin is defined by three components: protocol, e.g. HTTP, / versus HTTPS // host, e.g. example.com versus API.example.com versus sub.example.com, port, e.g. 80 versus 443 Vs, 3000. If any of these three components differ, the resources are considered to be from a different origin or cross-origin. The SOP states that a web page can only access data, scripts, or other resources that originate from the exact same origin as itself. For example, if you visit your banking website, https://mybank.com, the JavaScript running on that page can freely interact with other resources served from https://mybank.com, but it cannot, under SOP, make a fetch request to https://maliciousite.com and then read the response data programmatically. If it could, a malicious site could trick you into visiting it, then silently make requests to your logged-in banking session, read your account balance, and send it back to the attacker. The SOP is a crucial security measure that has safeguarded the web for decades. However, it's also incredibly restrictive for modern, distributed web applications. The problem SOP creates, and CORS as the solution. Modern applications rarely live on a single origin. Your Next.js frontend might be served from https app.example.com, but your API, even your BFF, might be on https api.example.com or https app.example.com/API. These are different origins. The host differs for the first, the path is different for the second, but the browser treats /API as a different resource path on the same origin as a general page. For CORS, it's if the protocol, host, or port differs entirely. Your dedicated backend might even be on https core-api.example.com. Without a mechanism to relax the SOP, your legitimate front-end application would be blocked by the browser from making necessary requests to your API endpoints on different origins. CORS is that mechanism. It's a system of HTTP headers that allows servers to explicitly tell browsers that they permit certain cross-origin requests. It's a controlled way for servers to opt in to allowing certain different origins to access their resources. How CORS works: simple requests versus pre-flight requests. CORS operations in the browser fall into two main categories. 1. Simple requests. Certain types of requests are considered simple by the browser and don't trigger the most complex part of the CORS handshake. These typically include HTTP methods, get, head, or post. Standard headers only, e.g., accept language, content type, with very specific values like application/xwww formal encoded, multipart /form data, or text plain. When a browser makes a simple cross-origin request, the browser sends the request directly to the server. The server processes the request and includes specific CORS headers in its response, most importantly, access control allow origin. The browser examines the server's response headers. If the access control allow origin header matches the origin of the requesting page, the browser allows the JavaScript on that page to access the response. If it doesn't match, or if the header is missing, the browser blocks the response from the JavaScript, resulting in a familiar CORS policy error in the console. 2. Pre-flight requests, the options method. For any request that is not simple, browsers perform what's called a pre-flight request. This happens before the actual request is sent. These non-simple requests include HTTP methods other than get, head, post, e.g., PUT, delete, patch. Requests that include custom headers, like an authorization header with a bearer token. Requests with content type headers that are not one of the simple ones, e.g., applications/JSON. The pre-flight request is a separate HTTP options request that the browser sends to the server. It's like the browser politely asking the server, "Hey, I'm from https app.example.com. I'm about to send a PUT request with an authorization header to you. Are you going to allow this?" Browser sends options, pre-flight. The request includes headers like access control request method, e.g., PUT, and access control request headers, e.g., authorization. Server responds to pre-flight. The server, if it allows the requested operation, responds to the option's request with CORS headers, indicating which methods, headers, and origins are permitted for the actual request. It might also include access control maxage to tell the browser how long it can cache this pre-flight response. Browser sends actual request. If the pre-flight response indicates that the actual request is permitted, the browser then proceeds to send the real PUT request. If the pre-flight response is negative or inadequate, the browser aborts the request before it even leaves the client, preventing potentially harmful cross-origin interactions. Key CORS response headers, server-side configuration. For your API on the server side, to correctly implement CORS and satisfy browser security checks, it must return specific HTTP response headers. Access control allow origin. This is the most crucial header. It tells the browser which origins are allowed to access the resource. Example, access control allow origin. https app.example.com allows only https app.example.com. Example, access control allow origin. Wildcard allows any origin use with extreme caution, especially if credentials are involved. For multiple specific origins, the server must dynamically set this header to the requesting origin if it's whitelisted, as you cannot list multiple origins in a single header, nor can you use with credentials. Access control allow methods lists the HTTP methods, e.g., get, post, PUT, delete, that are allowed when accessing the resource. This is particularly important for pre-flight responses. Access control allow headers lists the request headers, e.g., authorization, content type, xcustom header, that are allowed when making the actual request. Also important for pre-flight. Access control allow credentials. If the request needs to include user credentials, like cookies, HTTP authentication, or client certificates, this header must be explicitly set to true. Critical. If access control allow credentials is true, then access control allow origin cannot be. It must be a specific origin name. This prevents an attacker from making an authenticated request from any origin. Access control maxage specifies how long the results of a pre-flight request, the option's response, can be cached by the browser in seconds. This reduces the number of pre-flight requests for frequently accessed resources. Common CORS misconfigurations and risks. Incorrectly configuring CORS can lead to both security vulnerabilities and frustrating development issues. Overly permissive access control allow origin. Setting access control allow origin is acceptable for purely public APIs that require no authentication or send no sensitive data. However, if your API handles user-specific or sensitive data and is used with credentials, cookies, or authorization headers, using is a severe security risk. It opens up your API to potential CSRF attacks, where an attacker on any malicious site could trigger actions on your API using your logged-in user's credentials. Always use specific origins for access control allow origin in production for APIs that handle sensitive data or authentication. Missing headers for pre-flight. You might correctly handle GET or POST requests, but forget to configure your API to respond to options requests with the appropriate access control headers. This leads to browser errors as the pre-flight fails. Caching issues. Not setting access control maxage or setting it too low can lead to excessive options requests, impacting performance. Setting it too high means changes to your CORS policy take longer to propagate. Configuring CORS in Next.js and backend APIs. Let's consider our architectural setup. Next.js frontend browser, Next.js API BFF, Next.js API routes. No CORS issues here. Because your Next.js frontend and its API routes are served from the same base URL, e.g., https yourdomain.com. Requests from the frontend to /API/ are considered same origin by the browser relative to https://yourdomain.com. Therefore, you do not need to configure any CORS headers on your Next.js API BFF for requests originating from its own bundled Next.js frontend. Next.js API BFF server, dedicated backend API server. No CORS issues here either. CORS is a browser-enforced security mechanism. When your Next.js API BFF makes a request to your dedicated backend API, it's a direct server-to-server HTTP call. There's no browser involved in this leg of the journey. Hence, CORS policies do not apply. You do not need to configure CORS on your dedicated backend API for requests coming from your Next.js API BFF. Dedicated backend API, if directly exposed to external clients used by other frontends. If your dedicated backend API is also directly accessed by other client applications, e.g., a mobile app or another web frontend hosted on a different domain, then you will need to implement CORS configuration on that dedicated backend. It must explicitly allow the origins of those other clients. For a server-side framework, this usually involves adding a CORS middleware or specific route handlers. For example, in a generic Node.js Express server, you might use a package like CORS to easily configure allowed origins, methods, and headers. The key takeaway for our Next.js architecture: when using the BFF pattern, the beauty is that you largely push CORS configuration away from your dedicated backend and avoid it entirely on your Next.js API BFF for its primary front-end interaction. Any necessary CORS configuration becomes minimal and exists only when other external front-end applications need direct access to your dedicated backend. Your Next.js BFF acts as a protective shield, simplifying the cross-origin dynamic. CORS is a powerful and necessary security feature, not just an annoyance. By understanding how the same origin policy works and how CORS selectively relaxes it, you can accurately configure your services, avoiding both frustrating errors and critical security vulnerabilities in your interconnected web application. Our next step is to examine another powerful browser-enforced security mechanism, Content Security Policy, which further hardens your front-end against injection attacks. 10. Content Security Policy, CSP. Hardening your front-end. We've covered a lot about ensuring secure communication between your Next.js application and its backend, authenticating users, and managing sessions. But what about threats that originate primarily from the front end? The browser, for all its sophistication, can still be a vulnerable environment if not properly secured. This is where Content Security Policy, CSP, comes into play. Imagine your web application as a meticulously designed vault. You've secured the main door authentication, built robust internal mechanisms, authorization, backend separation, and established clear pathways, CORS, for legitimate entry. But what if a malicious actor could sneak in through a ventilation shaft or a hidden panel, and once inside, control what your vault's security cameras record or even override the alarms? This is analogous to injection attacks like cross-site scripting, XSS, where malicious code can execute within your user's browser, bypassing your careful server-side security. CSP acts as a powerful, browser-enforced security layer that significantly mitigates the risk of XSS and other code injection attacks by whitelisting trusted sources of content. It tells the browser, only load scripts, styles, images, and other resources if they come from these explicitly approved locations. What is Content Security Policy? CSP is an HTTP response header that web servers can send to web browsers. This header contains a set of directives that specify which resources the browser is permitted to load and execute on a given page. If a resource, like a script or an image, is not from a source explicitly allowed by the CSP, the browser will block it. This approach flips the traditional security model. Instead of blacklisting known bad actors, which is a losing battle as new threats emerge constantly, CSP uses a whitelisting approach, only allowing explicitly trusted resources. How CSP works: when a browser receives a web page with a CSP header, it parses the directives. Then, as it attempts to load any resource on the page JavaScript files, CSS style sheets, images, fonts, media, or even connect to external domains. It consults the CSP. If a resource's origin, domain, protocol, etc., is not explicitly allowed by the relevant directive in the CSP, the browser will block the resource from loading and executing. Report a violation to a specified reporting endpoint, optional, but highly recommended for monitoring. This means that even if a traditional XSS vulnerability were present in your application, e.g., user-supplied content containing script alert, XSS/script, the browser, under a strict CSP, would block that inline script from executing because it didn't come from an allowed source and is an inline script. Key CSP directives. A CSP header is a string containing one or more directives separated by semicolons. Here are some of the most common and important ones. Default SRC. This is your fallback directive. It defines the default policy for fetching resources like scripts, images, audio, video, etc., if no other specific directive is specified for that resource type. Example: default SRC self allows only resources from the same origin as the document. Script SRC specifies valid sources for JavaScript. This is crucial for preventing XSS. Example: script SRC self https trusted-cdn.com allows scripts from the same origin and a trusted CDN. Critical: avoid script SRC unsafe inline and script SRC unsafe eval. These directives should be used only as a last resort in legacy apps, as they reintroduce significant XSS vulnerabilities by allowing inline scripts and eval-like functions. Style SRC specifies valid sources for style sheets. Img SRC specifies valid sources for images. Connect SRC. This is vital for Next.js applications as it controls which URLs can be loaded using programmatic interfaces like fetch, XML HTTP request, WebSocket, event source. It directly impacts your API calls. Example: Connect SRC self https api.yourdomain.com allows your frontend to make API calls to your own domain and your dedicated API. Font SRC specifies valid sources for fonts. Frame ancestors specifies valid parent sources that may embed a page using frame, iframe, object, embed, or applet, useful for preventing clickjacking. Example: frame ancestors none prevents your page from being embedded anywhere. Object SRC specifies valid sources for object, embed, and applet elements. Recommended to set to none unless you specifically need these legacy elements. Base URI restricts the URLs that can be used in a document's base element. Recommended to set to self. Report URI/report to, highly recommended for production. These directives specify a URL where the browser should send JSON reports of CSP violations. This allows you to monitor and adjust your CSP without breaking legitimate functionality. Implementing CSP in Next.js. Since CSP is delivered via HTTP headers, you need to configure your Next.js application to send these headers with every page request. The most common ways to do this are via Next.config.js, headers option, for newer Next.js versions using the app directory router, or even the pages directory for all pages. This is the simplest and recommended approach for many use cases. You can define custom headers that will be applied globally or to specific paths. Example: conceptual. In Next.config.js, module exports, async headers, return, source, path, headers, key, content security policy, value default SRC self, script SRC self, style SRC self, unsafe inline, connect SRC self, https api.yourdomain.com, img SRC self data. Note: unsafe inline for style SRC is often necessary due to how React and many CSS and JS libraries inject styles. While it's generally best to avoid unsafe inline, its risk for styles is lower than for scripts. Via a custom server, if you're using one. If you've opted for a custom Node.js server, e.g., Express, running Next.js, you can add middleware to set the CSP header. This offers more dynamic control if needed. Dynamic CSP with nonces. a truly secure script SRC directive often doesn't allow unsafe inline. However, Next.js and React Hydration often generates inline scripts. The solution for this is to use a nonce, number used once. How it works. For every request, your server generates a unique, cryptographically strong random value, the nonce. This nonce is included in the CSB header. Script SRC self, nonce. The same nonce is then applied as an attribute to every script tag that is allowed to execute inline on that page. Script nonce equals random value inline code script. The browser will only execute inline scripts if their nonce attribute matches the one in the CSB header. This makes it impossible for an attacker to inject and run their own inline scripts without knowing the secret per request nonce. Implementing nonces in Next.js requires a slightly more advanced setup, often involving server-side rendering logic to inject the nonce into both the CSB header and the script tags. Common CSB pitfalls and best practices. Starting too secure. Implementing a very strict CSB from day one can easily break your website. Start with a more relaxed policy and gradually tighten it. Unsafe inline / unsafe eval. Avoid these keywords as much as possible for script SRC. They significantly weaken your CSB's protection against XSS. Explore nonces or hashes for inline scripts. Third-party scripts APIs. Remember to include all * external domains that your site relies on, e.g., Google Analytics, advertising scripts, embedded widgets, social media buttons in your CSB directives. Forgetting one will break functionality. Testing in report-only mode. Before enforcing a CSB fully, deploy it with a content security policy report-only header. This will instruct browsers to report any violations to your report query without actually blocking the content. This allows you to identify and fix legitimate violations during development and staging. Avoid inline style. While unsafe inline for styles is less risky than for scripts, it's still best practice to use external style sheets or CSS and JS solutions that don't generate truly inline styles unless unavoidable. CSB is not a panacea. CSB significantly reduces XSS risk, but does not eliminate it entirely. It complements other security measures like input validation, output encoding, and secure cookie practices. CSB provides a powerful, proactive defense against one of the most prevalent web vulnerabilities. By carefully crafting and enforcing a content security policy for your Next.js application, you add a critical layer of protection for your users, ensuring that only the content you trust is executed in their browsers. This is a crucial step in building truly bulletproof web applications, safeguarding them right at the client-side frontier. Our final technical chapter now turns to a broader range of API vulnerabilities that go beyond authentication, authorization, and network defenses. 11. Beyond auth. Common API vulnerabilities and strategic defenses. So far, we've laid a robust foundation for securing your Next.js APIs, focusing heavily on the critical pillars of authentication. Who are you? Authorization. What are you allowed to do? Building the secure BFF, and understanding crucial browser-enforced security mechanisms like CORS and CSB. These are indeed foundational. However, the world of API security extends far beyond just these concerns. Attackers are constantly looking for new ways to exploit applications. The Open Worldwide Application Security Project, OWASP, is a non-profit organization dedicated to improving software security. Their OWASP API Security Top 10 identifies the most critical API security risks. While many of the items we've already covered directly address some of these, it's vital to broaden our perspective and address other prevalent vulnerabilities that can plague any API, regardless of its authentication scheme. This chapter will introduce you to several common API vulnerabilities, distinct from the core auth and auth-z issues, and provide strategic defenses you can apply to your Next.js API routes and your dedicated backend. 1. Broken Object Level Authorization, BOLIS. Insecure Direct Object References, IDOR. The vulnerability. This is one of the most common and critical API vulnerabilities. It occurs when an API endpoint accepts an object identifier, like a user ID, product ID, transaction ID, from the client and retrieves data or performs an action associated with that object without adequately verifying that the authenticated user is authorized to access or manipulate that specific object. Scenario: imagine an API endpoint to retrieve user profiles, /API/users/profile/user ID. A legitimate user requests /API/users/profile/123 to view their own profile. An attacker, by simply changing the user ID in the URL to 456, could potentially access another user's profile if the API doesn't perform a server-side check to ensure that the authenticated user, 123, is indeed authorized to view 456. Impact: unauthorized access to records, data modification, or deletion leading to data breaches, privacy violations, and data integrity issues. Strategic defenses: always implement object-level authorization checks. For every request that involves an object identifier, the server-side logic in your Next.js API route or dedicated backend must verify that the authenticated and authorized user is sanctioned to access or modify that specific instance of the resource. This is sometimes called row-level security. Use random non-guessable object IDs. While this doesn't replace authorization checks, using UUIDs, universally unique identifiers, or other non-sequential IDs instead of sequential integers makes it harder for attackers to simply iterate through IDs to find other users' data. Principle of least privilege: ensure even authenticated users only have access to the data they absolutely need. 2. Broken function level authorization, BFLA. The vulnerability: similar to Bolus, but at a broader functional level. It occurs when an API allows a user to access functionality or endpoints that they are not supposed to, often by simply changing the API endpoint or HTTP method. Attackers can gain access to administrative functions, special user privileges, or other sensitive operations. Scenario: a regular user, client-side, might see a button for get/API/user/settings. An attacker might try sending a post request to post/API/admin/users/delete, hoping that the server doesn't check their role or permissions for that administrative endpoint. If the server only checks if the user is logged in but not their specific roles, the attack succeeds. Impact: unauthorized access to administrative panels, privilege escalation, and system compromise. Strategic defenses: strict role-based access control, RBAC. Every API endpoint and every HTTP method handler within that endpoint should have explicit, server-side checks for the user's role and associated permissions. Not just is authorized, but is authorized for this specific action. Minimize endpoint exposure. Only expose API endpoints that are strictly necessary. Avoid putting admin functions on publicly accessible API routes if they can reside in a more restricted backend. Centralized authorization module. Implement a consistent, reusable authorization module that checks user roles and permissions before allowing access to specific routes or functions. 3. Mass assignment. The vulnerability. This occurs when an API automatically binds client-supplied data, e.g., from a JSON request body to internal data models or objects, without proper filtering or whitelisting of what properties are allowed to be updated. Scenario: a user updates their profile using put/API/user/profile. The request body might contain name, John Doe, email, john@example.com. If the API model also has an isadmin property and the attacker sends name, John Doe, email, john@example.com, isadmin, true, a vulnerable API might automatically update the isadmin property in the database, granting the user administrative privileges. Impact: privilege escalation, data corruption, and unauthorized state changes. Strategic defenses. Explicit property whitelisting. When accepting data from a client for updates or creation, explicitly define and whitelist the properties that are allowed to be updated. Never implicitly bind all incoming payload fields to your data models. Data transfer objects, DTOs. Use DTOs within your API routes backend that represent only the fields the client is allowed to send or receive. Map the incoming data to these DTOs, then map the DTOs to your internal database models, ensuring only allowed fields are copied. Separate models. Maintain distinct data models for your internal database schema and your external API schema, allowing for granular control over what's exposed and mutable. 4. Excessive data exposure. The vulnerability. An API reveals more data than is strictly necessary for the client to function, often due to a lack of proper filtering of sensitive information before sending the response. Scenario. Your API retrieves a user's entire record from a database, which might include hashed passwords, payment details, internal IDs, or other PII. Even if your frontend doesn't display this data, if the API sends it, an attacker inspecting the network traffic can see it. Impact: sensitive data exposure, privacy breaches, and potential for further attacks using the exposed information. Strategic defenses: filter output explicitly. Only return the minimum required fields in API responses. Don't simply return select from your database. Use data projection transformation. Map your internal data objects to specific response models that contain only public or non-sensitive information for the given API endpoint and the user's authorization level. Sensitive data masking redaction. For truly sensitive fields, e.g., credit card numbers, social security numbers, mask or redact them before sending them to the client. 5. Lack of resources and rate limiting. The vulnerability. APIs are typically designed to serve many requests. However, without proper limits on how many requests a client can make within a certain time window, or the volume of data that can be processed, an API can be subjected to various forms of abuse. Scenario: an attacker repeatedly attempts to guess passwords on a login endpoint, brute force attack. Or they flood an endpoint with requests to exhaust server resources, denial of service, DoS. Or they might make excessively complex queries that consume disproportionate processing power. Impact: account takeover, denial of service, resource exhaustion, increased infrastructure costs. Strategic defenses: rate limiting. Implement rate limiting on all API endpoints. This restricts the number of requests a user or an IP address can make within a defined period, e.g., 100 requests per minute. This should be done at your Next.js API BFF level and/or your dedicated backend. Throttling. Beyond just limiting, throttling can also slow down responses if a user exceeds a certain threshold. Resource quotas. Limit the size of request bodies, the number of items in a batch upload, or the depth of queries, e.g., for GraphQL APIs. Account lockout mechanisms. For authentication endpoints, implement account lockout or progressive delays after a certain number of failed login attempts to deter brute force attacks. Web application firewalls, WAFs. A WAF can provide a layer of protection against various types of attacks, including DoS, by filtering malicious traffic before it reaches your applications. 6. Security misconfiguration. The vulnerability. This is a broad category encompassing errors like insecure default configurations, incomplete configurations, misconfigured HTTP headers, open cloud storage, or unnecessary features being enabled. Scenario: using default credentials for databases or admin panels, leaving debug mode enabled in production, having outdated security patches, misconfigured CORS or CSB policies, or exposing sensitive directories in web servers. Impact: wide range of compromises, including unauthorized access, data breaches, and system control. Strategic defenses: secure defaults. Always configure everything with security in mind from the outset. Change default credentials. Principle of least privilege configuration. Only enable features and ports that are absolutely necessary. Disable unnecessary services. Regular security audits. Continuously review your server, network, and application configurations. Patch management. Keep all software operating systems, frameworks, libraries, databases up to date with the latest security patches. Environment parity. Ensure your development, staging, and production environments are as similar as possible in terms of security settings, avoiding production-only vulnerabilities. 7. Improper assets management. The vulnerability. Failure to properly inventory and secure all API endpoints, old API versions, debug endpoints, or expose API documentation that reveals sensitive information. Scenario. An old V1 API endpoint that was presumed unused still exists and has critical vulnerabilities, or private API documentation is accidentally committed to a public repository. Impact. Exploitation of unknown vulnerabilities, information disclosure, and system compromise. Strategic defenses. API inventory. Maintain a comprehensive and up-to-date inventory of all your API endpoints, including their purpose, version, and security requirements. Version control. Clearly version your APIs, e.g., /API/v1, /API/v2, and deprecate old versions gracefully but firmly, eventually removing them. Scan for exposed assets. Regularly scan your public-facing infrastructure for accidentally exposed files, directories, or old unused endpoints. Secure documentation. If you host API documentation, ensure it's protected and not accessible to unauthorized users. Building a defensive mindset. Successfully defending against these broad categories of API vulnerabilities requires more than just technical fixes. It demands a defensive mindset. Developers must learn to think like an attacker. Constantly ask, how could this be misused? Or what if this input is malicious? Embrace shift-left security. Integrate security practices throughout the entire software development lifecycle, from design and coding to testing and deployment. Validate everything, always. Never trust input, never trust the client, and never trust external systems without verification. Practice security by design. Build security into the core architecture of your Next.js application and its associated backend, rather than trying to bolt it on as an afterthought. While intimidating at first, addressing these vulnerabilities systematically and integrating them into your development process is key to building truly resilient and secure Next.js APIs that stand up to the ever-evolving threat landscape. In our final chapter, we'll consolidate all these learnings into a holistic strategy for architecting and maintaining your secure Next.js application. 12. Building a secure Next.js API. A holistic approach. We've journeyed through the complex landscape of API security, exploring everything from the fundamental distinctions between authentication and authorization to the intricate workings of OAuth, JWTs, secure cookie management, and the architectural power of a backend-for-frontend. We've also equipped ourselves with browser-enforced defenses like CORS and CSB, and broadened our understanding to encompass a wider array of API vulnerabilities beyond just access control. Now, it's time to bring all these pieces together. Building a truly bulletproof Next.js API isn't about implementing a single magical solution. It's about adopting a holistic, layered security approach, often referred to as defense in depth. This strategy acknowledges that no single security measure is foolproof, and if one layer is breached, subsequent layers are there to prevent a full compromise. The secure Next.js API architecture. A recap. Let's visualize the recommended secure architecture we've built throughout this book, starting from the user's browser, moving through your Next.js application, and reaching your core backend services. User's browser, frontend, runs your Next.js client-side application. Relies heavily on browser-enforced security mechanisms like CORS to allow communication with your BFF, and CSB to prevent client-side injection attacks like XSS by whitelisting trusted content sources. Stores authentication artifacts, e.g., refresh token or session ID, in secure HTTP-only and same-site cookies, preventing JavaScript access and protecting against CSRF. Next.js API BFF, API routes, acts as the secure intermediary, receiving requests from your frontend. Orchestrates authentication, initiates OAuth OIDC flows, exchanges authorization codes for tokens, and manages secure cookie issuance, e.g., for refresh tokens. Manages refreshment, uses refresh tokens to obtain new, short-lived access tokens from the authorization server, keeping these tokens server-side. Proxies requests securely, forwards requests to your dedicated backend, adding the ephemeral access token and handling any secret credentials, like API keys, on the server, ensuring they never reach the client. Performs initial authorization validation. Can perform initial checks based on the validated refresh token or user roles before forwarding to the dedicated backend. Hosts other non-sensitive API routes for functionality that is entirely front-end specific and doesn't require direct interaction with the core backend, e.g., simple contact form submissions. Redis Session Store for scalable session token management. A fast, in-memory data store primarily used by your Next.js API BFF. Stores server-side session data for stateful sessions, or, more critically, maintains a blacklist/denalist of revoked JWTs, e.g., invalidated refresh tokens, allowing immediate logout and token invalidation. Dedicated backend API core business logic. Your hardened, separate backend service, e.g., Node.js, Python, Java, that houses your core business logic, interacts with your database, and handles third-party integrations. Validates access tokens. It receives short-lived access tokens, JWTs, from the Next.js API BFF and performs full signature verification, expiration checks, and claim validation. Enforces granular authorization. This is where the definitive, what can this user do? Checks happen based on the validated token's claims, roles, permissions, object ownership. Crucial for preventing bolus IDOR and BFLA. Manages sensitive operations. Handles database interactions, complex calculations, and sensitive third-party API calls, ensuring all associated secrets are securely managed, e.g., via dedicated secret management services. Implements input validation and output filtering. Rigorously validates all incoming data and ensures only necessary data is returned, preventing mass assignment and excessive data exposure. Rate limits and throttles. Protects against resource exhaustion and abuse. Database external services, the ultimate destination for your data and external integrations. It should only be accessible by your dedicated backend API, typically within a private network. This layered architecture provides separation of concerns, limits exposure of sensitive data and logic, and allows for independent scaling and iterative security improvements. Putting it all together. A secure request flow. Let's retrace the path of a typical secure authenticated request in this integrated system. User action. A user, already logged into your Next.js application, clicks a button to retrieve their profile data. Front-end request. The Next.js frontend sends an HTTP GET request to its local API endpoint, /API/profile. Automatic cookie inclusion. The browser automatically attaches the user's HTTP-only, secure, same-site refresh token cookie. BFF processing. Your pages /API/profile.js or app/API/profile/route.js. API route receives the request. It extracts the refresh token from the incoming cookie. It securely, server-side, uses this refresh token to obtain or refresh a short-lived access token from your authorization server. It checks your Redis blacklist to ensure the refresh token hasn't been revoked. BFF proxies to backend. The Next.js API BFF then makes a server-to-server request to your internal dedicated backend API, e.g., https://api.yourdomain.com/user/profile. This request includes the newly obtained access token in the authorization, bearer header. Dedicated backend authorization. The dedicated backend API receives the request. It validates the access token's signature and claims, e.g., exp, auth, is. It then performs granular authorization checks based on the token's claims, e.g., is userid 123 authorized to access this specific profile? Data retrieval and response. If authorized, the dedicated backend retrieves the profile data from the database, filters it to include only necessary information, preventing excessive data exposure, and sends it back to the Next.js API BFF. BFF response to frontend. The Next.js API BFF receives the data, possibly performs some final formatting, and sends it as a JSON response back to the user's Next.js frontend. The user sees their profile, never knowing the complex, secure choreography that just transpired. Beyond architecture, operational security. Even the best architecture can be undermined by poor operational practices. Secure development is an ongoing commitment. Secret management. Never hardcode sensitive information, API keys, database credentials in your codebase. Use environment variables, and in production, leverage dedicated secret management services, e.g., AWS Secrets Manager, Azure Key Vault, HashiCorp Vault, that integrate with your deployment pipeline. Secure development practices. Input validation and output encoding. Continuously validate all user input and properly sanitize all output to prevent injection attacks, XSS, SQL injection. Always use HTTPS. Encrypt all traffic in transit. Obtain SSL/TLS certificates and enforce HTTPS via redirects, e.g., HSDS headers. Secure defaults. Configure your servers, databases, and third-party services with security in mind. Change default passwords, restrict network access. Automated security testing. Static application security testing, SAST. Integrate tools into your CI/CD pipeline to scan your code for common vulnerabilities, e.g., dependency scanning for known vulnerable libraries. Dynamic application security testing, DAST. Spin up your application in a test environment and use tools to scan for runtime vulnerabilities, e.g., OWASP ZAP, Burp Suite. Penetration testing. Engage security professionals to rigorously test your application for vulnerabilities from an attacker's perspective. Logging and monitoring. Implement comprehensive logging across your Next.js application, BFF, and dedicated backend. Use centralized logging solutions, SIEM systems, to collect, aggregate, and analyze logs. Monitor for unusual patterns, e.g., repeated failed login attempts, unusual API call volumes, access from suspicious IPs that could indicate an attack. Set up alerts for critical security events. Incident response plan. Have a clear plan for how to detect, respond to, mitigate, and recover from a security incident. Knowing whom to call and what steps to take before a breach happens can significantly minimize damage. Regular updates and patching. Keep all your software operating systems, Next.js, Node.js runtime, libraries, databases, up to date with the latest security patches. Vulnerabilities are discovered constantly. Timely patching is crucial. Stay informed. The threat landscape evolves rapidly. Follow security news, subscribe to security advisories, e.g., from OWASP, NVD, and continuously educate yourself and your team on new vulnerabilities and best practices. Conclusion: the continuous journey of security. Building a secure Next.js API is not a one-time task, it's a continuous journey. As applications evolve, new features are added, and the threat landscape shifts, your security posture must adapt. This book has provided you with a comprehensive toolkit, an architectural blueprint, and a strategic mindset to approach Next.js API security effectively. By embracing defense in depth, carefully implementing authentication and authorization best practices, leveraging secure architectural patterns like the BFF, and diligently applying operational security measures, you are well equipped to build applications that are not just functional and performant, but truly bulletproof. Remember, security should always be designed in, not bolted on. It's an integral part of application quality, user trust, and business success. Happy and secure coding.